Alright, so in this video, I'll introduce you to variable length compression, and we'll see some basic results on variable length compression, what is achievable and what is not achievable. Let's start with the basic problem. So in a previous video, you've seen fixed length compression, and we saw the source coding theorem, which said that at least for an IIT source, if the block length is large enough, if the file size is large enough, then you can achieve a rate close to the entropy of the source, right? And we'll aim to prove a similar result in this particular video. So the difference between fixed length source coding and variable length source coding are twofold. So first, the length of the compressed file need not be fixed. In variable length source coding, the compressed file size can depend on the realization of the file, and also, unlike unlike fixed length source coding, where we can tolerate a small probability of error, in variable length source coding we do not tolerate any error. So we want to be able to reconstruct the file exactly at the output. Okay, so for now, let us consider the problem of compressing a file, or maybe even a single symbol. So we have a random variable x. So x comes from some set script x, and this is distributed according to some known distribution px. So at least for now, we will assume that the encoder and decoder know the input distribution px. Okay, and the goal is to compress this to a file, a binary file of arbitrary length. So the set of all possible binary sequences is denoted 0, 1 raised to the star. So this includes binary sequences of length 0, 1, 2, 3, all the way up to infinity, right? So the encoder or the compressor takes x as input and outputs a binary sequence, the compressed sequence, and when this is fed to the decoder or the decompressor, it's expected to give x as the output, right? Okay, so the decompressor should output x exactly, and our goal is to minimize the expected length. So if L of x denotes the length of the code word corresponding to x, then our goal is to minimize L of x in expectation. So for any given code, let's denote a code by calligraphic C. So a code essentially corresponds to an encoder and a decoder. It's a pair of sequences, right? So the expected length achieved by a particular code is defined as the expected length of the code word corresponding to the random variable x, right? And our goal is to keep L of C as small as possible. So let's see. So what properties do the encoder and decoder have to satisfy? What properties does the code have to satisfy? So one class of codes is the so-called class of non-singular codes. This is one of the most basic properties that you would expect in any compressed in any compression scheme. So given an input, it's supposed to give the output exactly. So an encoder is basically a map from the input alphabet to the set of all possible binary sequences, and of course what we want is that two symbols should not have the same code word, because otherwise you wouldn't be able to decode at least one of them correctly, right? So a code is said to be non-singular if every pair of symbols have different code words. So for all symbols x1 and x2, we have the property that f of x1 is not equal to f of x2, right? So this is the most basic property that one would expect. Now, if you think about it deeply enough, then you realize that the optimal non-singular code corresponds to the following. So remember, our goal is to minimize the expected length, and optimal code is one which minimizes the expected length, right? So if we have symbols x1, x2, x3 up to say xm, where m is the number of symbols in the alphabet, then the optimal non-singular code would be the following. You order the symbols in decreasing probability. So let's assume that x1 has probability greater than x2 and so on, all the way up to xm. So p of x1 is greater than or equal to p of x2, which is greater than or equal to p of x3, and so on. So obviously, if you want to minimize the compressed length, then sequences of higher probability should be assigned smaller code word lengths. And there's a very simple way to do this. So for the first symbol, obviously you assign the code word which is just 0. For the second symbol, you assign the code word 1. For the next code word 0, 0, and then 0, 1, 1, 0, and so on. So all possible sequences of length 2, and then all possible sequences of length 3, and so on. Right? So you do this, and obviously this is this sequence is non-singular. You can, so given the code word, you can recover the transmitted symbol exactly, and of course this it's easy to convince yourself that this code will have minimum expected length. So any other code will have an expected length which is larger than this particular code. But now, do you see that there's some problem with this code? So in particular, let's suppose that I want to encode a sequence of symbols. So here, what this code does is that given one particular symbol, we know how to encode it well enough. But what if I want to encode the concatenation of multiple symbols? So suppose I want to encode some sequence, let's say y1, y2, y3, right? And basically what the way I want to compress this particular sequence is to use the same code to encode y1, then encode y2, and then encode y3, right? So let's, without loss of generality, let me just assume that the symbols over here, just to avoid some confusion, let me assume that I have m symbols, and the symbols are 1, 2, 3, 4, and so on up to m, right? And the code word corresponding to symbol 1 is 0, the code word corresponding to symbol 2 is 1, for 3 it is 0, 0, for 4 it is 0, 1, and so on, right? So suppose that I want to encode say 1, 2, 4, okay? Then the corresponding code for the code word for 1 to 4 would be the concatenation of the code words for 1, 2, and 4, right? So it would be 0, 1, 0, 1, right? But if I just concatenate these, then there is no way to recover the original sequence from these code words. And why is that? Because I don't know where exactly each code word ends and the next code word begins, right? So if someone gave you a parsing that the first code word is 0, the second code word is 1, and the next code word is 0, 1, if someone gave you this parsing, then it would be easy to reconstruct 1, 2, 4 from 0, 1, 0, 1. But otherwise, it's difficult, right? So it could be that if I look at a different parsing of the same sequence, then I get another valid code word. So it would be just 4, 4, right? So unless someone gives you this parsing, these commas, the locations of these commas, there's no way to reconstruct the actual source sequence, right? And this is a fundamental problem with this particular code, right? And in practice, no one really gives you these commas. So somehow I want to be able to encode even if someone does not give me the locations of these commas, I should still be able to recover the original sequence. Right? So in general, just non-singularity is not a good enough condition. So a uniquely decodable code is one where is defined in the following way, such that so for all sequences x1 and x2, so the first sequence could be x11, x12, by notation, x21, so on, x2, say L, it's an L length sequence, and the second, x1 L, and the second sequence is x1 2, x2 2, and xm2, right? So if we define the extension of a code to be the concatenation of the code words of the corresponding code, so f of x1, x2, x3 up to xl is equal to f of x11 concatenated with f of x21, so on, right? So, and similarly you have the extension for f of x1, x2 up to xm. So a particular code is uniquely decodable if the corresponding code words are different for different sequences. So if x11, if the sequence x1 is different from the sequence x2, then the corresponding the code words corresponding to the extensions are different. Is not equal to x. Okay, so that's what we mean by a uniquely decodable code, and this basically ensures that even if we are not given those commas, we'll still be able to recover the original sequence, the original message sequence, or the raw file. Okay, so this is fine. So we'll define an even stronger condition. We'll define what a prefix-free code. A prefix-free code is one where the code word of corresponding to one particular symbol is never a prefix of the code word corresponding to any other symbol. So a code is prefix-free if for any pair of symbols x1, x2, x, f, the code word corresponding to x1 is not a prefix of the code word corresponding to another symbol. So what do I mean by a prefix? So for example 0010 and 00. So here if these are two code words, then this code word is a prefix of this code word, right? Because of course, so that's pretty obvious. So 000 is not a prefix of 0010, right? Okay, so here's a question for you: can a code be uniquely decodable but not prefix free? So it should be obvious that every uniquely decodable code is non-singular. Every prefix-free code is uniquely decodable and hence also non-singular. Clearly, every non-singular code is not uniquely decodable. We just saw that through an example. But is every uniquely decodable prefix-free, or do there exist uniquely decodable codes which are not prefix-free? Right. So here's an example of a code which is uniquely decodable but not prefix-free. So consider the code words 0 and 01. Right. So this is obviously not prefix-free because 0 is a prefix of 01. But given any sequence, you can always say whether the sequence is what the source sequence is. So let's suppose that alpha has code word 0 and beta has code word 01. So if you have 0 0 1 0 0 0 1 0, then what would the corresponding sequence of source symbols be? So what does this code word correspond to? This code word would correspond to the parsing 0 0 0 1 0 0 1 0, right? So given any particular sequence, there exists only one such unique parsing into code words. So this would be alpha alpha beta alpha alpha beta alpha, right? So you don't have two different ways of parsing into code words. Now the difference between a uniquely so this code is uniquely decodable but not prefix free. So prefix free code is also called an instantaneous code, and the reason is the following. So suppose that you see a symbol 0, right? You're not sure if the code word ends at this particular point, right? Because it's possible that so let's suppose that the first code word symbol that you see is 0, right? You at this point if you've only seen 0 and you don't know, and let's suppose that you've not seen the rest of the symbols so far, at this point you're not sure whether this is the code word corresponding to alpha or beta, right? Because you must see what the next symbol is. So this would correspond to the first symbol would be alpha if the next symbol is also 0. If the next symbol is 1, then the first symbol would be beta, right? So in some sense, you need to look into the future, one step into the future, in order to decide whether the current symbol is alpha or beta, right? But on the other hand, if you have a prefix free code, then you know exactly. So if you've seen so let's consider the code where alpha corresponds to 0, you have beta corresponding to 1 0, and gamma as code word 1 1, right? So at any point you know that okay, this is the code word has not ended, but you don't need to look into the future to decide whether a code word has ended or not. So if the first symbol is 0, then you're sure that the first symbol is alpha, right? But let's suppose that it's 1 0, right? So this is not, so if you've seen only the symbol, if you've seen only the symbol 1, then of course you're not sure whether this is beta or gamma, but the code word has anyway not ended yet. There is still one symbol left to go. So then if you see 0, which is the code word corresponding to beta, you know that this is the code word corresponding to beta and you don't need to look into the future. Whereas here in this particular example, if you see just a 0, then you know that this could be a code word for alpha, but you're not sure. It could be the code word for beta as well, right? So although you might have reached the end of the code word for alpha, you're still not sure, because you may need to look at the first code word bit of the next symbol to decide whether the current symbol has been recovered or not. So So for these reasons, it's generally preferable to design prefix-free codes rather than uniquely decodable codes which are not prefix-free, because you can decode these sequences instantaneously. And in fact, there are codes for which you may need. So in this particular example over here, you just need to look one step in the future in order to decide whether this has in order to decide the current symbol. You can in fact construct codes where you may need to look infinitely many steps into the future till the end of the entire sequence in order to decide what the first symbol is. Right? Okay. So therefore we will mainly be interested in designing prefix-free codes, right? Because they're much easier to encode and decode. And in fact, every prefix-free code can be characterized in terms of a code tree, right? So let's consider some code, say 0, 0, 1, sorry, not 0, 1, maybe 1, 1, 0, and 1, 0, 1, right? So these are two codes. These are three code words corresponding to some code. I can represent this in terms of a binary tree. So 0, 1. So this leaf corresponds to the code word. Let's say we have three symbols, alpha, beta, and gamma. So this is the code word corresponding to alpha, and 1, 0, 1 would correspond to gamma, and 1, 1, 0 would correspond to beta. Right? So we can always construct this code tree, and a code is prefix. So this can be, in general, you can define this. You can define such a code tree for any code, not necessarily prefix free. But one property that a code tree has is that so you can identify a node in the code tree corresponding to the code word for a particular symbol, right? So there's a one-to-one map between the nodes of the code tree and the source symbols alpha, beta, gamma. So a code is prefix free if and only if in the code tree every code word is a leaf in the code tree. So it's not an intermediate node, right? So no code corresponds, so no node corresponds to the descendant or the ancestor of any other code word. So for example, if you have 0, 0, 1 and 1, 0, 1, right, then 0, 0, 1, 1, 0, 1, 1, 1, right? So you have three code words, and these correspond to these three nodes, right? These red nodes. And clearly in this particular example, you have one code word which is an ancestor of another code word. So this is an ancestor of this, or this is a descendant of the other one, right? And therefore this code is not prefix free. Right. So this observation will turn out to be very useful in deriving certain properties of prefix-free codes. So this is a necessary and sufficient condition for a code to be prefix-free. Well, it's an almost sufficient condition for a code to be prefix-free. So we can define So we have certain necessary and sufficient conditions for any code to be prefix-free. And the necessary condition is the following. So no matter which prefix-free code you choose, if you look at the lengths of these code words, suppose that L of x is the length of the code word corresponding to symbol x, then the sum over all possible x of 2 to the minus L of x should always be less than or equal to 1. So this is a necessary condition for any prefix-free code, right? And you also have a sort of sufficient condition. It's not fully sufficient, but it tells you how do you construct a prefix-free code. So suppose that you have a set of positive integers. So corresponding to each symbol in the alphabet, you have a positive integer L of x, such that they satisfy this particular condition. So this condition is called the Kraft inequality. This is the Kraft inequality. So if a sequence satisfies the Kraft inequality, then we can construct a prefix-free code with lengths L of x. Right? So the length of the code word corresponding to x would be L of x. So as long as we have a set of integers which satisfy these properties, the Kraft inequality, we can always construct a prefix-free code with length L of x. Okay, so let's briefly see why this must be the case, right? So as we noticed earlier, corresponding to any prefix-free code, we can construct the binary tree, the code word tree, right? Maybe this is some binary tree, right? And maybe these are code words, right? Right, so maybe these are code words corresponding to, so this corresponds to some prefix-free code, right? And this is a valid prefix-free code because no code word is a prefix of any other code word. So no code word node is an ancestor or a descendant of any other code word node, right? So given this particular code word tree, let us look at the extension of this tree. So suppose that the maximum length of the code word is L max. Right? So it's the maximum overall possible x of L of x. Let's look at the maximum code word length. In this particular example that I've drawn, the maximum length is 1, 2, 3, 4, right? So the maximum length is 4. Right? Let us extend each node, let us extend all these leaves all the way up to L max. So this, right? Let's look at the extension, right? And in this extension, so this is what I call the extended tree. So this is what I call the extended tree, and look at the number of leaves which are descendants of each code word, right? So for example, for this particular code word, we have 4 descendants, right? These 4 are descendants in the extended tree. Corresponding to this, there are 4 code words in the extended tree, 4 leaves in which are descendants in the extended tree. For this, there are 2 leaves which are descendants in the extended tree, and so on, right? Now since this is a prefix-free code, you should see that the descendants of any particular code word and the descendants of any other code word, they don't intersect. So each code word will have distinct descendants, right? So this, that much is obvious. So but in the extended tree, can you tell me what the number of leaf descendants are for any particular code word? I want you to pause the video and think. So given this particular, given the code word tree, and these red nodes are the code words, you look at the extended tree where you add more edges till it goes all the way up to L max. You go all the way up to depth L max, and now you want to find the number of leaves which are descendants corresponding to each code word, right? And I want you to find, and suppose that a code word has length L of x, it has length L of x, then what is the number of leaves which are descendants of this particular code word? Pause the video and think about it for a moment. Okay, so the number of descendants, it's easy to see that the number of descendants is 2 to the L max minus L of x. So this is the number of leaf descendants corresponding to any code word. Okay, so that's pretty much obvious. And then, so now that we have this, right, we have this, but what is, right, and so if the code is prefix free, then all the descendants are distinct, right? The descendants don't, the set of descendants of one particular code word do not intersect with the set of descendants of any other code word. But what is the total number of leaves in this extended tree? It is 2 to the L max, right? So this is the total number of leaves in the extended tree. And since there's no intersection in the set of descendants, the sum over all possible x of the number of descendants of each, the number of leaf descendants of each code word should be less than or equal to 2 to the L max, the total number of leaves in the extended tree, right? So if you divide both sides by 2 to the L max, you get the Kraft's inequality, which simply says that summation over x of 2 to the minus L of x should be less than or equal to 1. Okay, so this was okay. So we proved one part of Kraft's inequality, that any prefix-free code should satisfy this Kraft's inequality. So now suppose that we have a set of integers which satisfies Kraft's inequality. Suppose we have L1, L2, L3, and so on, all the way up to Lm, and these satisfy 2 to the minus Li is less than or equal to 1. Then how do we construct a prefix-free code? Well, the idea is similar to what we have done previously. You first draw the extended tree, right? You look at L max, the maximum or all possible I of Li, and then draw the extended tree up to depth L max, right? Let's suppose that the code word lengths given to us are, say, 1, 2, and 3. Okay, let's assume that this is what is given to us, right? So does this sequence satisfy Kraft's inequality? We have half plus 1/4 plus 1/8 plus 1/8, and this, yes, and this does satisfy Kraft's inequality. So what you do is you start from the very left. So the first code word, you start from the very left. So the code word length is 1, and you stop at this point, and you immediately discard all this entire point, right? Right? So this 0 would be the code word corresponding to the first symbol, corresponding to length 1. So this is the first code word. The second code word must have length 2. So you ignore all the descendants of the other code words, and then you traverse here, and then always traverse towards the left if you can go, right? Otherwise you traverse to the right. So this is 1 0. The code word must be of length 2, right? So 1 0. And now we want two code words of length 3. So the next is here. We can't go to the left, so you go to the right. And now can you go to the left? Yes, you can. So go to the left. So 0. We have one code word of length 3, which is 1 1 0. And similarly for the code third, we have 1 1 1. And this is a prefix-free code. So this is an algorithmic approach to showing that as long as a set of lengths satisfies Kraft's inequality, there exists a prefix-free code with code word lengths equal to these. Okay, and this is a very powerful tool, right? And we'll make use of this property over and over again. Right? So these were sort of necessary and sufficient conditions on the code word lengths of any prefix-free code. But now let's go back to our original problem, where our goal was to design a prefix-free code with the minimum expected length. So even before we know how to construct an optimal prefix-free code, let us see what is the best that an optimal prefix-free code can do. Now we can show that the minimum expected length of any prefix-free code is always bounded between the entropy of x and the entropy of x plus 1. Okay. Now I won't prove the lower bound. I won't prove this inequality. You can find this in chapter 5 of the book by Codeword and Thomas. But I'll anyway prove this property because it's constructive and it will make use of what we've just seen now. Okay. So note that so we've seen only one approach to constructing a prefix-free code, right? So we know only one way to construct a prefix-free code. As long as we have a set of lengths which satisfies the Kraft inequality, we know how to construct a prefix-free code, right? So as long as I can determine, so corresponding to each x, if I can find an L of x such that 2 to the minus, such that summation over all x 2 to the minus L of x is less than or equal to 1, then I'm good. Then I know how to construct a prefix-free code. So all I need to do to show the existence of one prefix-free code achieving this property, I just need to construct the lengths which satisfy the Kraft's inequality, right? So let me choose L of x to be the seal of log 1 over p of x. Right? So clearly this is less than or equal to log p of x plus 1, log 1 over p of x plus 1, and this is greater than or equal to log 1 over p of x, right? Okay. So firstly, does this satisfy Kraft's inequality? Let's see. So we know that log L of x is greater than or equal to log 1 over p of x, right? And since L of x is greater than or equal to log 1 over p of x, minus L of x is less than or equal to log p of x, right? Okay. So basically minus L of x is less than or equal to minus log 1 over p of x. So minus L of x is less than or equal to log p of x. Now what about summation over all possible x 2 to the minus L of x? This is less than or equal to sum over all possible x 2 to the log p of x, but 2 to the log p of x is just p of x. So this is summation over all possible x of p of x, which is 1. So this set of code word lengths obviously satisfies Craft's inequality. So there exists a prefix-free code. We can construct a prefix-free code with these particular code word lengths. Now, what is the expected code word length corresponding to this code? The expected code word length is summation over all possible x of p of x L of x, but L of x is ceil of log 1 over p of x, which is less than or equal to h of x plus 1. And therefore we have this particular inequality. Right? So we now have a constructive approach to achieve a rate which achieve an expected length which is close to the entropy. So it's off by one particular bit. And when do we have equality? So we'll have equality if every p of x is 2 to the minus some integer z of x. So if every p of x is equal to 2 to the minus z of x for some integer z, then this inequality becomes an equality. So or in other words, not this doesn't become an equality, then ceil of log 1 over p of x will be equal to log 1 over p of x, and the rate or the expected length would be exactly equal to the entropy, not entropy plus 1. So we can achieve entropy only when p of x is 2 to the minus some integer for all possible x, and such a probability mass function is said to be dyadic. Okay, so now that we've seen this, let's go back to the original problem that we started off with in the first lecture, right? So our goal was to construct good codes for large sequences. So for sequences of length n, we want to construct a good code. So right now we have constructed a good code for individual symbols, right? So and for a large sequence, our goal is to construct a good variable length code. A variable length code with 0 error, and we want to minimize the rate, and the rate is defined as L of xn divided by n, right? So the expected L of xn divided by n. So now suppose that we used this particular code. So by the way, this is called the Shannon code. So this is called the Shannon code. So suppose that we use the Shannon code over all possible sequences of length n, right? So we don't concatenate the code words anymore. We construct a code on xn with, so this has probability mass function pxn, which is the product over all I from 1 through n of pxi. So if the sequence is IID, then this is just a simple product distribution, right? So if we construct a code for xn, then the expected length is obviously less than or equal to h of xn plus 1, right? But this is also greater than or equal to h of n by n. But if the sequence is IID, we know that h of xn is n times h of x. So R is between h of x and h of x plus 1 over n. Yeah, but note that to achieve this, we are coding on blocks. We're designing a Shannon code for a block of symbols, so a block of n symbols, right? So this is different from what we discussed just a bit earlier, where you design a code for each of the individual symbols and concatenate. So here we are not doing a concatenation of the code words corresponding to each symbol. We are designing a separate code for the sequence itself. So our new alphabet is script x to the n, right? And the distribution is pxn, right? Whereas earlier we would have constructed a code for script x and with distribution px, and if we are given a sequence xn, we would just concatenate the code words corresponding to each symbol. But if we want to achieve this particular rate, then this is the best that we can possibly hope to achieve. Whereas if we use this particular approach where we design a code for each symbol, we do symbol-wise encoding and concatenate the code words, then the expected length would be n times h of x plus 1, which is n h of x plus n. So coding over blocks gives us a great benefit over coding over symbols. You can reduce the redundancy, or you can reduce the expected length by at most n minus 1, right? Okay. So clearly, if we design, if we do blockwise encoding using the Shannon code, then we can achieve a rate which is close to h of x. So as n tends to infinity, r is equal to r tends to h of x, right? And therefore, for variable length codes, we can achieve r star. So the best possible rate that one can hope to achieve is equal to the entropy, right? And we can't do any better than this, because we've already seen that for any prefix-free code, the expected length is always greater than or equal to h of x. Right. So now let's see what happens if, so in many applications we don't know what the true distribution is, right? Because I mean, who gives that to you? What you instead do is typically estimate the distribution by looking at the empirical frequency of letters and use that as a proxy for the true distribution. But in general, this could be, depending on the number of samples you have, your estimate, the empirical estimate, could be different from the true distribution, right? So and therefore this leads to some loss in the rate, and in fact we can characterize this exactly. So suppose that we have a random variable x which is distributed according to some distribution p, but instead we design a Shannon-Fano code assuming that the distribution was q of x, which is where q is different from p. So q is some other distribution. Maybe q is your estimate of the true distribution, whereas the true distribution is actually p. So in that case, the expected length that you can achieve using the Shannon-Fano code is lower bounded by the true entropy h of p plus small loss. So this is the additional redundancy that is introduced, and this is equal to the KL divergence between p and q, right? And it is upper bound, and the expected length is upper bounded by the entropy plus the KL divergence plus 1, right? And this is pretty easy to prove. You can try working this out for yourself. Just choose L of x to be equal to this, and then simplify, and you would get h of p plus dpq. Okay, so that's it for this lecture. In the next lecture, we'll see some code constructions, and we'll see different code constructions and see which one is the best. We'll see more practical schemes, and see which one you would want to use in different scenarios.